Now, whenever you have of course we are still talking about the Taylor series expansion, but whenever you have example like this, that you have a polynomial, then you will always of course in this case also you can perform the method that we have previously seen, and I will show you how to do that. We will just use the definition, and the definition says that the function of f of z will be f of z0, the Taylor series expansion, plus the double prime and the bracket squared upon 2 factorial plus the triple prime of the function, the cubed of the bracket upon 3 factorial, and so on. This is the definition about z equals z0. Okay, and just like in the previous case, we will first find the functions and the required derivatives. So this is the function, and the first derivative of this will be minus 1 upon bracket squared, and now you will just follow the simple rule. So this will be 2 by the brackets cubed and so on. And of course, alright, so I forgot to say that it is about z equals 1, so that's your z0, and therefore you will find that f of 1 will be 3, then f prime of 1 will be minus 1 upon 3 square, which is 9. F double prime of this will be, oh, I'm so sorry, I made a mistake here, 3 cubed, so that's 27, and this is 81. We can make some simplifications here. Okay, all right, so once we have them, we can just plug these values into the series, and you see that so alright, so then the first derivative is minus 1 by 9 upon z minus 1 upon 1 factorial, no need to write, plus 2 by 27 into z minus 1 square upon 2 factorial, plus yes, we have this, so minus 2 by 27 upon z minus 1 cubed upon 3 factorial, and so on. And you will perform even more simplifications over here, that you will open the brackets and you multiply and you do some cancellations and you just come up with the most simplest version. You can also expand this square term by a minus b whole square, and then you multiply these things inside, and just get the most simplified version of this expansion, which is I'm not performing here, but that's not a rocket science, so we can do that. So this is the one way of solving the problem, which we have already seen, that you are given a function you just using the definition itself, so in which you need these derivatives and you find them about the particular point, plug in the values and do the simplification. That's the end. This is the answer to your Taylor series expansion, which is absolutely fine. This is also a correct method, but I am saying is that we do have an alternative method for polynomial involved functions. So whenever you have a polynomial, you can use some alternative method, and which is the very much recommended because we will need to use them again and again even in solving the Lorentz series expansion. So we should and we must get kind of comfortable with this alternate method, because they are the most useful means this is the most useful method. And let us see what do we have in this. In this, what new thing we will do is that we are asked, you see here, that we are asked to find the expansion about z equals 1. Okay, so what do we do here is that about z equals 1, so that means z minus 1 equals 0, and you put this equal to t, which is equal to 0, that is z minus 1 equals t. I have put the z minus 1 equals t value here. Okay, so therefore your z will become t plus 1. Now why am I doing this? That you will know at the end of the result, I mean at the end of the problem. So you just know that whenever you are given to find the expansion for particularly for the polynomial, and which I don't know whether you can see here or not, I will write a little bit bottom here in the box. Whenever you are asked to find at z equals z0, you always convert it into this form, and then this z minus z0 becomes t. So it will be effectively t equals 0. So this whole thing will become t. So this is what I have done. I have to find about this. I converted into in this form, and I call this whole thing as the t, and everywhere in place of z, now I can put this value. Alright. Also, we will be using the binomial expansion rules, a couple of rules here, and which says that I hope you know this, that 1 plus x to the minus 1 is 1 minus x plus x squared minus x cubed, and so on. And when you have 1 minus x to the power minus 1, then you have 1 plus x squared plus x cubed, and so on. Okay. Alright, so these are the binomial series expansion formula, a very simpler one which we are going to use in this alternate method. Okay, so now let us build up our problem. We are given f of z equals 1 upon z plus 2, but we are going to use z minus 1 equals t, therefore z equals t plus 1 for this term. So the function of t will become, in place of z, I will write t plus 1. In place of z, I have written t plus 1, plus 2 will remain as it is. Alright, only I have replaced this z by this, nothing else. Okay, and now let us do some simplification, that this will become t plus 3. Okay, now you see here that you need to know a couple of facts about this binomial series expansion, and it is that in both this formula there is one condition that the mod x must be very less than 1. Only in that case you can apply this formula. So this x term here and here are very smaller than 1. It cannot be greater than 1. They cannot be bigger than 1. In that case you cannot apply this formula. So this is the very important condition. You should know, you should remember that this is valid only for the case when x is smaller than 1. Here we have t plus 3. If we want to apply any of this formula, mostly we are going to we are going to apply this, since we have plus in between them. But then we want 1 plus something kind of thing. Only then we can apply this. So we want to have a structure which are closer to this. In order to get 1 plus something, we have two alternatives. Either we can take t common, so then you will have 1 plus 3 by t, or we can have 3 common, then we have 1 plus t by 3. Okay, so now which of them is correct? This is the question here. Okay, so you see that here 3 is greater than 1. Okay, so you calculate that 1 upon 3 will be 0.33 something. So that means this term is smaller than 1. Okay, this term is smaller than 1, and therefore we are going to use this possibility and not this one. So we will take 3 outside, and we have t by 3 plus 1. I am just rearranging them. 1 plus t by 3, and then this is nothing but 1 plus t by 3 to the minus 1. And now I have that 1 plus x to the minus 1 formula, okay, in which this term is smaller than 1, and therefore now I can perform the rule of that series expansion. So 1 plus x to the minus 1 is 1 minus x plus x square and so on. So this will be 1 minus t by 3 plus t by 3 squared minus t by 3 cubed plus so on. So you just simplify. I am taking 1 by 3 inside, so this become t by 3 squared plus t squared by 3 cubed minus t cubed by 3 to the power 4 and so on. And now you just, in place of t, you put the original value. What was the original value of t? We saw that t is equal to z minus 1. So you just put it back. So it's 1 by 3 minus z minus 1 upon 3 squared plus z minus 1 squared upon 3 cubed minus z minus 1 cubed upon 3 to the 4 and so on. So that's the answer to this series expansion, and that is what you would find in our previous method also. If you could simplify, then you will have, here you already seen z minus 1, z minus 1 squared, z minus 1 cubed. If you would open this bracket up and you would simplify, you will get the similar result. But you see here that with smaller steps, we have actually got the result very quickly. So this is something, therefore I said that in case you have a polynomial kind of functions, it is always advisable to use this alternate method instead of this one. Both of them are going to give the correct answer, of course, but this is more recommended. Even there will be some problems in which you will be very much needed to use only this method and not the other one, when you have a very complicated functions, because then it becomes very complicated to find the derivatives and plug in the values and simplify the series. Alright, so in other cases you can always use the previous problem, the previous method, in which you just put the values, the derivatives, into the definition of the Taylor series expansion. But whenever you have polynomial, you will use this alternate method. Okay.